Welcome back, everyone, to Hot Interconnects. And my name is Dan Pitt. I'm chairing the subcommittee that deals with keynotes and the panel, ably assisted by Alan Benjamin and Pavel Shamis. And so this year we have 3 keynote speakers. We have an outstanding panel coming up in an hour. And I am especially thrilled to welcome Tony Chan Carusone from Alphawave Semi to be our keynote speaker this afternoon. Tony is taking time away from a family vacation overseas to join us today. And I couldn't be happier about that. Tony is quite an exceptional innovator. He's been a professor at the University of Toronto for a couple of decades. He spent some time at IBM as a visiting researcher and scientist. And he's now also, in addition to being the professor, he's the CTO of Alphawave Semi. Now, Alphawave Semi produces, IP modules mainly having to do with interconnection. They also do will deliver some silicon, and they're focused a lot these days on the chiplet economy and how you interconnect these chiplets, whether they be processors or memory or something else, to really accelerate the AI revolution. Now, Tony gave a keynote at the Chiplet Summit in February this year in Santa Clara, California, here in Silicon Valley, where I live. And it was the best presentation I have seen on any subject in at least 10 years. So when we started organizing Hot Interconnects on this topic, I went first to Tony and pleaded with him, can you come and speak with us? He said, I'm on vacation. I said, make it work somehow. He has agreed to do so. He's had quite a career of innovation, really focusing on integrated circuits. And interestingly, to me especially, it's not just processors, and it's not just interconnect, and it's not just digital, but also analog ICs. Some of you might have noticed, many of you probably have not noticed, that there is starting to emerge a rise of analog computing again. And I have little doubt that Tony will be one of the key voices of this movement when it gains momentum. Right now, he's focused on making Alphawave Semi succeed, and I can't wait to hear how he says they will do that. So, Tony, the floor is yours.
Thanks so much, Dan, for all those kind words. Hope I can live up to it. Just one quick correction on the bio. I haven't spent any time at IBM, actually. I've been at Intel, though, and many other large and small companies. I hate for folks at IBM to come and get me and call me on that. So
I meant Intel. Sorry.
It's all good.
Okay.
But no, thanks so much for the warm introduction. That was lovely. I'm the Chief Technology Officer at Optical right now, but really I started researching die-to-die links that have now proven critical to enabling the proliferation of chiplets at the University of Toronto. Remember, they're over 10 years ago. And now at Alphawave, we're building these chiplets for AI, and we really have it's given me a front row seat in seeing how chiplet architectures are unleashing all the potential for AI. Alphawave recognized some time ago these massive trends in the industry that we're going to inevitably move everyone towards chiplet architectures. And so Alphawave has been positioned early on to be in that space. And it's really gratifying to see all the transformations now taking place after all the R&D over so long a period of time. And it's personally gratifying to be here and share a bit about that with you. So obviously the topic of the conference is interconnect, and I've been working on connectivity challenges in one form or another my whole career. And now as I'll speak about, connectivity's really become absolutely key, both to scaling AI and also to this maturing chiplet ecosystem. So first, I'll just start out taking a look at some of these high-level trends that AI is driving. So there's a lot of silicon that's being developed right now that's intended to fill fab lines in the most advanced CMOS nodes for many years to come. And it's all for deployment in data centers to support AI scaling. So keep in mind, the majority of the world's large data centers are run by hyperscalers that operate these massive warehouses of compute around the world. And within each of these facilities, routers and switches move data between compute and over to storage. So these data centers now have scaled out to the point where many of them are now distributed across multiple facilities that are connected together to form a single virtual data center. And at the same time, there's this trend towards locating some cloud computing in so-called regional data center locations that are closer to end users to increase their responsiveness and realize the full potential of network rollouts using 5G and beyond wireless technologies. And so you hear a lot of talk about AI at the edge. And I find that can be confusing for a lot of people because AI at the edge means a few different things in different contexts. It can mean really lightweight inference in mobile or very low power devices to do simple tasks, even right in the phones and sensors that are the sources and the originators of data. Um, and it can mean more capable inference on personal computers in the home or office to make sense of all that data privately and securely. But another key aspect of AI at the edge are these smaller regional compute facilities that are still centralized, but they're in many more locations throughout urban settings so that complex and high performance inference and even training in some cases can be performed responsibly and with low end-to-end latency for those end users. So this represents a lot of new high performance computing and connectivity needs, both within these locations and to tie them back to the massive hyperscale data centers that warehouse even larger centralized computing and networking. So the scaling of AI has really supercharged the rollout of a lot of new silicon infrastructure. It's accelerating data center upgrades and new construction, and it's also presenting some new challenges both inside the data center and beyond to support this AI at the edge. So already, just with this picture, you can see how AI requires a ton of compute, but that it's enabled and underwritten by connectivity everywhere, whether it's over kilometers of optical fiber or, as we'll talk about, over the wiring between chiplets that are less than a millimeter in length. So the whole story really begins with the proliferation of data. This plot on the right shows worldwide data center data storage in zettabytes. And what you see in the early 2010s is sort of linear growth in the amount of data that was being stored worldwide. And that's because humans were generating that data. So you saw this linear growth. But then at some point, there was this transition to machine generated data. And there we see exponential growth in the amount of data in the world. So it's just sensory data, cameras, financial transactions, imagery, scientific collection of massive amounts of data, and then computer analysis on all that, yielding yet more data. And so that gives rise to this exponential increase in the amount of data. And so that drove renewed interest in intelligent computing that parse all that data and reinvigorated a lot of R&D. And that interest combined with progress on compute silicon led to breakthroughs in AI and what captivated us all when we saw ChatGPT burst on the scene, and just the amount of complexity in this AI processing has just grown very quickly ever since with all the investment. So we see the number of parameters in these models increasing, and really there's some recommender systems with sparse models that have many more parameters even than these. So as a result of all this AI scaling, compute infrastructure is being pushed to its limits on several fronts. So first, performance. Here we run up against the reticle limit that limits the size of a monolithic die, and thereby it limits the amount of compute integrate. Energy also poses limits. So there's thermal considerations. How much energy dissipation turned into heat can we actually dissipate and control the temperature of the silicon? There's also the operating cost that's required to power all that compute. And then there's just the limits imposed by environmental considerations with all that energy consumption. But then scaling AI sustainably implies not just controlling energy consumption, but also controlling the cost of compute. That's really essential to allowing scalable AI. If you think about the kind of investment that's needed to deploy AI at large scale, you're talking about tens of thousands of servers with many GPUs each, and each of those costing, let's say, tens of thousands of dollars. You very quickly get to massive dollar figures. So the stakes are huge, and whenever you have that kind of money on the table, there's a lot of incentive for R&D into new technologies that can really improve things. So that's what we're seeing. And chiplets are one of the key technologies that's attracted interest and investment in order to address all these pressures. But I just want to double click for a second on the power consumption issue when it comes to AI hardware. This is a problem that motivates me personally. I don't think many of us get out of bed in the morning eager to go to work and work hard trying to lower the cost of a chip by a penny or two. But working towards lowering the energy consumption of compute is a really great positive motivation for a lot of us. So power consumption of compute and in data centers has been on the radar as an issue for several years, of course, but AI has really supercharged it to a whole new level. So if you consider, the example of an advanced GPU, right? This one from NVIDIA shown here, that's an obvious example. Training on hardware like this exercises a lot of the chip for a large fraction of the time and continuously for weeks or even months on end. So it's consuming more energy than traditional compute servers and data centers, which are generally over-provisioned to handle peak loads. So moreover, this silicon is very expensive, and as a result, it's unlikely to be left idle for a long period of time when you're spending that much money, capital investment on it. So it's unlike traditional compute infrastructure, the data center, which can be over-provisioned for those peak loads. A chip like this consumes hundreds of watts. By the time you put it into a rack with all the associated power delivery, networking required to feed it data and keep it busy, all the cooling hardware, you're thinking about over a kilowatt of power consumption per GPU in total. So when you consider, let's say, take this example here, and imagine that NVIDIA delivers, say, 1.5 or 2 million of these in 2024 alone. So once commissioned, those GPUs will be consuming as much as an entire large US city. And that's just the energy consumed by one AI processor chip from one company in 1 year. And those are the kind of numbers that are not even necessarily the latest and greatest processors, which might consume significantly more than that. We're starting to talk about AI factories that are going to house vast stores of these processors that are liquid cooled, powered by neighboring nuclear reactors, all to enable this future of AI. And if you look at the statistics around this, it's really staggering. In Ireland, for example, data center power is expected to go from about 15% of total electricity consumption to about 30% in the next few years. But globally, we're talking about it almost increasing from 2022 levels by the time we get to 2026 to possibly over 1,000 terawatt hours of energy consumption in data centers in 2026. So the International Energy Agency specifically calls out technology improvements that are going to be crucial to moderate the surge in energy consumption from data centers. So even assuming that all the R&D is successful, their best case estimate is still a 30% increase in data center energy by 2026. So an emphasis on low power design, again, it's one of the things that really animates me personally. Whatever we do to reduce power in these applications is going to translate into tremendous benefits for us all. The performance of AI has progressed over the last couple of decades with advances in both hardware and software. Now, actually, the early seminal work in AI predated the availability of the hardware that was needed to really allow for its beneficial use. If you go back, say, 15 years ago, AI was run as software on traditional server-grade general-purpose CPUs. And there was a long AI winter for decades leading up to this plot, during which progress on and interest in AI was relatively low. But that doesn't mean processing power was standing still. Moore's law was fueling steady improvements in compute power, but it was being directed to other. We even saw the birth of some early chiplet technology in that time with CPUs that combine multiple dies into a single package to afford improved performance. But what really marked the end of this AI winter and sparked the next wave of AI progress was a famous AlexNet paper in 2012 that popularized the use of GPUs for AI processing. Around then, we transitioned to GPU-based architectures that are massively more parallel than CPUs, with dedicated hardware for implementing the mathematical computations that underlie deep learning. But as we scale the amount of compute that we need from teraflops petaflops, we need even more specialized hardware that can deliver the compute with a lower energy footprint. So that's led to the creation of custom AI devices that are specially built for specific models and specific types of data. So all the major hyperscalers now have announced their own processor programs for this. And many of these have already been through multiple generations. And this is kickstarted a new arms race of a sort where hyperscalers are designing and implementing their own AI engines while also continuing to use a lot of industry standard GPUs. But those customized AI processing engines are optimized for their specific models. The way I think of it, properly designed bespoke silicon can always deliver a better combination of high performance and low power than general purpose and low cost than general purpose processors that are have to be made necessarily for general purpose use cases. So there have been a few quantitative data points that have emerged showing significant improvements in the performance per joule of energy consumption that can be offered by these custom silicon solutions for AI, improvements of up to even 200%. So optimized hardware is really seen as a key tool for continued performance improvements and unlocking further advances in AI over the coming years. And remember, it's also all about cost. In order to scale AI sustainably, we need solutions that offer those performance improvements with lower silicon cost as well as lower energy costs. Those high-end GPUs cost tens of thousands of dollars today, and with hyperscalers requiring hundreds of thousands of AI accelerators, we're talking about billions of dollars in investment. So interestingly, we've had this long-standing trend of compute chips to move to higher and higher energy consumption, but that's now being reversed. We see it by the latest generations of some of these custom silicon solutions for AI, which generally consume less power. I think this is an interesting recognition and indication of the importance of power consumption in the future of compute. So, clearly these very high levels of investment are not sustainable, nor is the carbon footprint that current compute solutions are leaving. So, some new technology paradigms are going to be essential to the path forward. We've spoken a lot about these AI accelerators so far, but it's not just AI accelerators where custom silicon solutions are proving beneficial. There's also several large chips that benefit from chiplet architectures on the custom networking side. Custom networking solutions are also a key ingredient for sustainable AI scaling. And now in this AI arms race, there's a desire for new, very complex, customized chips every 12 months. But chips of that scale and complexity typically take 18 to 24 months to really design, verify, fabricate, test, and so on. So designing with chiplets really is proving to be the only path forward to iterate on these new hardware solutions and provide improved performance on the cadence that's being demanded to support AI scaling. So with that motivation, here's just a quick outline for the rest of the talk. We'll talk a bit about the role of chiplets in AI compute, talk about how scaling AI goes hand in hand with scaling connectivity, and look at what's needed to really enable this new chiplet ecosystem. So first, the role of chiplets for AI compute. So I'm going to take as a starting point for this discussion a monolithic solution. That's one for which all the logic and all the I/O circuits are implemented on a single die over here. Presumably, it's in a very advanced CMOS technology, 3 nanometer, 2 nanometer. And so let's think about a solution like this and look at its benefits and drawbacks. So for a lot of years, the industry is really focused on the benefits of monolithic integration. And these were, of course, real and significant benefits as we went from millions to billions of logic gates on a single die. We could pack more memory, more peripheral functions, and so on. So, in a lot of respects, it may seem counterintuitive now that we talk about the drawbacks of monolithic integration. But remember that now we're talking about full reticle-sized chips with massive R&D and mask costs. And so there's several drawbacks of implementing such large ASICs monolithically. First, you're stuck with everything in one technology if you're monolithically integrating it. So things like DRAM have to be outside the package. That's why we've now got HBM, which are like memory chiplets that are co-packaged alongside processors and can be implemented in a different technology. Second, this main die is so complex that it requires the collaboration of many companies on different parts of the chip design typically. So there's processor IP, interface circuits, other functions that are designed as separate IP blocks, and integrating IP developed by different teams of people necessitates a bunch of added time for that integration, verification, and it adds some risk and cost to the design of the chip. The third point here is monolithic solutions are limited, as we said, by the maximum reticle limit die size that we can build. And if you're pushing up against that reticle limit, your yield is most likely suffering. And that's going to also drive up cost. In a monolithic solution like this, you're implementing those I/O transceiver circuits in the most advanced bleeding edge technologies, which is where you want all that logic to be. But those I/O circuits may not necessarily benefit from being there. And so you're putting a lot of extra effort and risk into that design. And it may also slow down your time to market and increase the design cost. Finally, you're limited in your flexibility here. You have to design that central chip there to handle whatever situation you throw at it. You have to design it with enough memory interfaces, all the I/O circuits you might need for some worst case use case. And all that has to be provided in every chip. When what you'd really like to do is amortize all that design effort over many different use cases. So inevitably, a monolithic solution ends up over-designed in some respects for some or all of those different use cases. So another issue with monolithic implementation of things like AI processors, we can call them, whether they're GPUs or TPUs or LPUs or whatever acronym you want to use, we can call them XPUs, is that bandwidth density can become an issue, especially in the coming years. So if you consider a next generation XPU that requires, let's say, 50 terabits per second of aggregate I/O bandwidth to keep all that logic busy, if that logic tile is near the reticle limit, let's say, it's going to have something like 50 millimeters of die edge available on the east and west sides of the die. If we assume that the north and south sides are occupied by HBM memory. So that implies about 1 terabit per second per millimeter of bandwidth density escaping these east and west sides of the dies with those general purpose I/O transceivers that have to handle any kind of connectivity channel that you might throw at it. That might be doable, but it's a challenge. It's a significant challenge. And again, what's the roadmap there going forward to the next generation beyond that? At some point, this starts being a significant challenge as well. So with chiplets, the industry can deliver higher performance, lower power, and lower cost by putting the processors in their latest and greatest 3 nanometer, 2 nanometer CMOS technologies, implementing them on smaller tiles, and then connecting them with die-to-die low latency interfaces. The I/O connectivity for things like PCI Express or Ethernet interfaces are moved to possibly older generations of CMOS technology on separate I/O tiles or chiplets. And then we can compose each of these systems in package to a target workload by mixing and matching the I/O tiles, the memory, the amount of memory, and the amount of compute power that we need in that package. So by disaggregating that large monolithic compute and networking chip into chiplets, we can increase the total amount of compute that we can put in a single packaged part, but at the same time, we can reduce the cost of the device by as much as 40%. There's better yield for these smaller chiplets than full reticle size chips. And there's, again, the potential to use perhaps some older CMOS technologies for parts of the design that don't benefit from the bleeding edge and most expensive CMOS technologies. Moreover, by allowing the I/O and the cutting edge compute chiplets to be developed and pre-validated independently, each can proceed on its own timeline with its own roadmap without the high risk, high cost, and long design and verification time that's required to assemble it all onto one chip at each generation. So chiplets, again, they also give us that additional freedom for some extra fan out in a package and might actually provide a path to higher total I/O bandwidth in and out of the package. So if you combine all these items, the benefits are clear overall, and that's why chiplet architectures are being used for virtually all the large compute and networking chips that are entering design today. Key point I want to emphasize here, last key point on this picture, is that this chiplet technology is clearly underwritten by another form of connectivity. It's the die-to-die connectivity. These are dense, low power, low latency interfaces between chiplets that allows this whole thing to perform as if it's effectively one massive chip. Those are absolutely key. So in summary, modern AI silicon solutions have these two key ingredients. There's compute. That means a lot of high performance CPU cores or processing elements in the most advanced logic, and connectivity. So that means all the connectivity need to network together all that compute, networking interfaces, memory interfaces, and indeed the die-to-die interfaces for these multi-chiplet systems in package. And all that's being assembled, all that technology is being assembled onto a common packaging substrate using chiplets. And essentially, again, key point is that chiplets are essentially the only way to affordably scale compute and connectivity performance on this timeline and with this cadence that's being demanded by this current AI arms race. So how do the benefits of a chiplet design paradigm translate into affordable and environmentally friendly compute? Well, if we take these benefits that we talked about, which we talked about 40% cost savings, say 25 to 50% power savings for AI applications, scaling them across the millions of AI accelerators that are going to be deployed in data centers and ultimately across the globe. The total cost and power savings that are achievable here are staggering. We're talking about billions of dollars and tens or even hundreds of gigawatts of power savings. So people sometimes ask whether chiplets are really going to take off. And generally, my response is twofold. First, it's already happening. As I said, the majority of new design starts for very large complex chips that I see are already being planned using chiplets. And second, it's sort of inevitable just given this very fast cadence of hardware upgrades that's now being demanded. So all the benefits of a chiplet design paradigm we've talked about, including reduced design time, reduced risk, all that can only be realized if we have these die-to-die interfaces that allow multiple chiplets to interface with each other seamlessly. So for compute and memory, that means HBM interfaces. That has an aggressive timeline for upgrades as well. We're moving from HBM3 now to HBM4, moving to denser IOs for those interfaces on more advanced packaging technologies. For the interfaces between logic tiles or over to the IO chiplets, UCI Express, UCIe is the predominant interface standard right now. These interfaces do represent some overhead compared to a monolithic integrated design. And so we need to minimize the overhead associated with these UCIe interfaces. So those interfaces would ideally consume near zero power, introduce near zero latency, and have a bandwidth density that's essentially comparable to what is obtained from on-die wiring. But that's a really tall order. I remember when I first started working on die-to-die interfaces over 10 years ago, I had colleagues from across academia and industry that really didn't understand my interest in the topic. To a lot of them, it seemed like these interfaces were sort of child's play compared to the really high-speed serialized interfaces, where at the time there were new modulation formats and new equalization techniques that were being heavily researched, and I was participating in that research too. It was certainly very interesting, but it was clear to me that these die-to-die interfaces represented a different kind of challenge, one that required this combination of high performance, low power consumption, low cost, and really one with tremendous potential for impact. And again, we're now starting to see that impact realized. So we just want to quickly walk through the key metrics for these die-to-die interfaces, and I'll give you a little feel for where things are by reference to UCIe, which again is a predominant open standard for die-to-die connectivity. First is bandwidth density. So there we see a clear path to achieving die-to-die connectivity with a bandwidth density exceeding 10 terabits per second per millimeter of die edge. That's really the key metric there. Energy efficiency, There, we're talking about certainly sub-picojoule per bit energy consumption, really less than half a picojoule per bit, and even much lower for more advanced packaging technologies. The latency of these interfaces is measured in clock cycles, like individual clock cycles, or like a very countable, very few number of core clock cycles. And when we talk about the reach of these things, obviously it's very short. It's within package links, but the ability to handle diverse packaging environments gives flexibility in your use cases. And that's really important for a chiplet ecosystem to take off, is having that robustness that you know that these die-to-die interfaces will work, even if there's some complexity introduced, and then the reach of the interconnect needs to be a little bit longer. So that's also emerged as an important metric here. And then there's a collection of characteristics that are more difficult to quantify, but are also really essential for these technologies. So it's their availability. Have they been demonstrated with performance across many CMOS technologies? Are they interoperable? Are they reliable? These are all things that benefit from some standardization, so that there's some agreed upon data rates, bit error rate targets, agreed upon packaging approaches, and so on. But these are all the key ingredients really that are needed for these die-to-die interfaces to enable the chiplet ecosystem. As I mentioned before, I think a lot of people have mistakenly thought that these die-to-die interfaces are easy to design, because after all, compared to Ethernet or PCI Express interfaces, they do operate at relatively slow serial rates. But again, remember, these interfaces are very, very dense, and the desire is for them to consume no power, no area, and to operate seamlessly. And that's a challenging combination. So in particular, there's, I think, three key aspects in the design of these die-to-die interfaces. First, their signal integrity, and key challenges there include managing crosstalk across the dense buses and compensating for any interconnect loss that arises. Second, there's maintaining power integrity. Because these are very small, dense interfaces, there's limited area available for power supply decoupling, so that presents power integrity challenges. And variations in packaging technology and dense signal routing complicate the ability to deliver power in and out of these circuits through the package. Now, finally, clocking is a challenge. You've got a wide bus on these interfaces, and so you need low power and low jitter clock distribution. And you need to be able to align the clock and data with enough accuracy so that these links are robust. So next, I'll talk about how connectivity is helping and fueling the scaling of AI. So far, we've talked a lot about the compute aspects of AI, but really compute and connectivity go hand in hand. So I want to look at how AI is reshaping data center networks. So we see pictured here a traditional data center network, but it's evolving. So these traditional networks are those that connect traditional compute servers, and they carry relatively short-lived streams of data via some combination of optical and electrical links. And so for these networks, a flexible architecture is preferred, with multiple layers of hierarchy with some redundancy incorporated. So the deployment of AI is certainly accelerating and diversifying these networks. For example, we just see higher aggregate amounts of data traffic flowing around, and that's leading to a demand for more optical connectivity, displacing electrical links in some use cases in order to achieve higher data rates. We also see an increasing emphasis on low power here to stay within the thermal budgets of these racks. But a really transformative thing is also going on with the introduction of AI acceleration clusters. There is even more growth being driven here. Sitting within that front-end network behind some servers are AI accelerating clusters interconnected by their own so-called back-end networks. These back-end networks are what allow the AI accelerators to access each other's memory directly and seamlessly. So that traffic is put on its own dedicated so-called back-end network to isolate it from the vagaries of the front-end network demands, which may rise and fall with various priorities depending on incoming requests for compute the front-end network. So these back-end networks have some unique requirements. So, for example, large training workloads running over there create sustained high bandwidth traffic. And the traffic on that backend network generally flows in more regular patterns and therefore doesn't necessarily require the same types of packet by packet switching as the front end network. When things are working properly, they operate with pretty high activity, and low latency is really critical because remember, you're trying to just draw from memory as if it was your own. So what that means is that these backend networks tend to have a flatter hierarchy that allows for fewer hops and thus lower latency. And similarly, that switching there has to be non-blocking because blocked traffic leaves expensive AI compute sitting around underutilized while it's waiting for data to show up. So because of these unique characteristics, the performance of the whole network can be bottlenecked by even one link that has frequent packet losses. So again, like robustness and reliability of the networks is even more critical over here. Any inefficiencies in the network, such as latency or packet loss, can significantly slow down training jobs and waste that really expensive AI acceleration resource. So there are some unique aspects here. And in the AI arms race, these AI acceleration clusters are growing rapidly. They're gone from hundreds to thousands to tens of thousands of AI accelerators. And that scaling is happening along two dimensions. We sometimes talk about scale up, which refers to adding more resources, in this case, AI accelerators, to a single AI server to increase its compute capacity. And whereas scale out involves adding more systems or more servers to the architecture to spread the workload across more machines. And both scale up and scale out are happening simultaneously, so really dramatically increasing the amount of connectivity needed. In addition, each of those individual AI processors are becoming more powerful in all the ways that we talked about earlier in the talk. So each one is demanding more and more bandwidth. So the result of this is a really dramatic increase in connectivity requirements. Distributed learning is increasingly of interest for training AI models because it's privacy preserving and decentralized. So this is an approach that can be used to train AI models without sharing sensitive information across institutions. So generally speaking, the idea here is to train models locally on devices and only share model updates with a centralized server and not the actual raw data, underlying data itself. So for example, different healthcare institutions can contribute to training a shared model on distributed data without directly exchanging the data. So that again helps with data security and privacy. But obviously approaches like this and other research directions that are emerging in AI rely even more so on connectivity. So this drive for more and more connectivity doesn't appear to be stopping anytime soon. So in sum, what does the rollout of AI and all the scaling mean for data center connectivity? Well, I'm trying to summarize it here. First of all, more data flowing, higher per lane data rates are demanded. At the same time, networks are scaling up and out to larger and larger clusters. And we're trying to maintain flat network topologies with high rated switches to reduce latency. Put those together, and that in turn leads to a proliferation of optical connectivity because you're having to traverse larger distances, higher per lane data rates, and that's where at some point electrical interconnect runs out of steam. And I'll just make one more point to illustrate how critical connectivity is to the whole enterprise. Once an AI training run starts, data really needs to flow continuously throughout the network. And unlike traditional networking, remember, there's not a lot of redundancy to reroute around failed elements. The latency that's associated with some retry and resend requests, even on a single link, can bring a training run to its knees, costing millions of dollars. So we literally hear reports of engineers praying for the success of one of these training runs as it's being launched. So the robustness of the connectivity is absolutely more important than ever. So I'll next talk a little bit about the key connectivity technologies, and I want to take a look at where it sits in all that hardware. So to do that, we can just take a look inside of a server. Actually, a traditional compute server has a lot of the same building blocks that you're used to seeing in an ordinary PC. There's CPUs, maybe more than one, because it's a high-performance server, let's say. And it's got memory and storage, and it's got a network interface to talk to other servers. So PCI Express, as the name suggests, peripheral component interconnect, is relied heavily upon to connect these peripherals back to the CPU. And for the memory, of course, there's typically some flavor of DDR would be normal. And an AI compute node has a lot of the same parts. There's still CPUs there to orchestrate all the activity. But the key point is the addition of all these GPUs that are added to accelerate AI computations. Now, these, although they're labeled GPUs here, they're not really graphics processors when it comes to AI. They go by many names. We can call them XPUs to keep it generic. But those XPUs have large amounts of their own separate memory that must be accessed constantly to fetch and store the data that's used frequently for those neural network computations. And so to handle more powerful networks that perform more powerful AI, we need more and more of these XPUs with readily accessible memory. So another key distinction between an AI compute node and a traditional data center server is the inclusion, again, of this additional network interface to the so-called backend network. So as mentioned, the purpose of that allows is that allows the GPUs to access each other's memory as if it was their own. So there's a suite of several key connectivity technologies here to enable this AI compute. And Alphawave, for example, we've invested in and developed all of them and trying to illustrate them here. I'm simplifying things here a bit, but just to make the point. So the front end network is still there to let the CPUs talk to each other, and that remains the purview of Ethernet primarily. The front end network interface card and any other peripherals are connected back to the CPU via PCI Express, as always. These are migrating from Gen 5 to Gen 6 now. Currently, the CPUs and XPUs access storage via PCI Express and perhaps CXL, which is sort of a variant or evolved form of PCI Express that allows for some lower latency and is of particular interest for storage interfaces. People are looking at the potential to provide direct connections between GPUs or XPUs and storage in the future. But for now, there's often use of PCI Express or CXL switches to increase the number of PCI Express interfaces that are available in one of these servers. The backend network over here is using either some kind of Ethernet or PCI Express based links, but often with some customizations to tailor it to those specific requirements that we talked about of the backend network. And then we've also got a lot of internal links between the XPUs and the CPU and the XPUs to each other. Again, these may be PCI Express or perhaps a customized version of PCI Express to suit the particular needs here. Finally, you've got HBM interfaces that we already talked about to allow the XPUs to talk to their own memory stores. And we've got the critical links between chiplets in any of these large systems and package shown here. So in sum, right, we've got this AI connectivity suite, PCI Express, CXL, Ethernet, HBM, and die-to-die interfaces, perhaps UCI Express, along with, in some cases, some customized versions of these tailored to the AI backend network. Another area that's being transformed by data center scale out are the connections to memory and storage. So the reports show here, this is a busy plot, but what's being looked at here is how servers are spending their time across a variety of jobs. And what this study showed here is that about a third of the memory in data centers on average is sitting around unused. And over here on the bottom, we see that a third of infrastructure spend in those installations is actually on memory. So that means over 10% of all the infrastructure spend in data centers is just sitting around unused. That's a lot of wasted money. And so there's every incentive to look at different ways of doing things. And so not surprisingly, one way would be to share memory and storage into centralized pools. Not surprising that that would allow for it to be used more efficiently. So we could recoup some of that wasted energy by moving to a disaggregated storage approach like this. But again, clearly this kind of approach relies more heavily on connectivity technologies that are going to allow for low latency access over the internet to this remote storage. The impact of AI is being felt, as I said, across the whole network. All that compute's creating a lot more traffic as we scale up and out to larger clusters. That's also increasing the physical length of the connections. And at these higher speeds and longer reaches, the bandwidth limitations of copper connections are becoming more and more of a limitation. So although copper continues to offer low cost and low power to establish the link, they simply can't deliver the required combination of speed and reach for AI scaling. So optics are seeing increasing use on both front-end networks and back-end networks. So today, that optical connectivity is delivered by and large by pluggable optical modules. Sometimes just called transceivers that are plugged into faceplates of servers and switches. So these are like small metal plugs that house really complex subsystems that themselves are being re-architected to meet the demands of AI, and that are also themselves seeing benefits from chiplet-based design approaches. So if we crack open that and look at the anatomy inside of one of these modules, we see increasingly that silicon photonics are being leveraged in combination with advanced packaging solutions to allow for a tighter integration of all the components in there to achieve some cost and power savings. Silicon photonics allows for the integration of all the optical components required for multiple lanes of optical communication to a single silicon chip. There's still a laser required, but critically, there can be fewer and simpler lasers than would be the case without silicon photonics. All the other optoelectronics are integrated on that silicon chip. This type of optical module is already having a big impact on coherent optical connectivity. So coherent optical connectivity is a technology that was previously reserved for really long-reach optical communications, originally just for transoceanic type links. But with this kind of architecture, then these components, that's allowing coherent optical links to address new applications for connectivity across only tens of kilometers. And as this technology continues to evolve, we see it having increased impact over even shorter reach optical links, ultimately even inside the data center. So this is a really classic use case for chiplet technology because it's necessarily heterogeneous, meaning you need different semiconductor fabrication technologies here. You've got advanced CMOS technologies for the digital signal processing. You need maybe some high speed and high voltage amplifier chips. And you need, of course, the photonic integrated circuits and lasers here. So really a great use case for using advanced packaging to combine different semiconductor technologies. Now, looking even forward, there's another opportunity for leveraging chiplet and advanced packaging technologies is co-packaged optics, which has had promise for many years. So as we've talked about, electrical links are a challenge at these higher data rates. Those pluggable optics I showed in the last couple slides still require some electrical connectivity between a large ASIC to the faceplate that I talked about, where the pluggable connectors are used. So CPO, or co-packaged optics, offers a vision where the optical connectivity comes all the way into the package. And a picture like this is obviously all about chiplets, since we already said the optical electronics require different fabrication technologies. Now, there's a few different ways this can play out, which I just want to go through quickly. But just keep in mind that all of these carry significant packaging challenges associated with attaching optical fibers and cooling the whole thing. The one shown here is so-called direct drive co-packaged optics, which relies on the same highly capable I/O DSP-based SerDes throughout the main logic pile to handle both short electrical, long electrical, and optical links. Then there's some analog broadband amplifiers that are included, typically fabricated in their own manufacturing technology on a separate chiplet, and the photonics themselves, yet another chiplet. So the good thing about this direct drive approach, where the main die directly drives the analog signals required for the optical link, are that same main logic chip can be used for both electrical and optical interfaces. But the bad thing is you're burdening that very large advanced logic chip by requiring it to house very advanced I/O transceivers. An alternative is so-called digital drive CPO. So here, die-to-die interfaces occupy less area on the advanced logic dies, and they interface to I/O chiplets that house either the I/O circuits required for electrical interfaces and, as required, optically capable I/O circuits that have a UCI interface on one side and can directly drive photonic ICs and optoelectronics on the other side. So with an approach like this, you have the potential to mix and match these logic tiles with different chiplets to create product variants with different connectivity demands. Once you go this route, you have the potential for tremendous bandwidth density on those over those die-to-die interfaces to the logic chiplet. We talked about 10 terabits per second per millimeter here on these interfaces and beyond. But the challenge and opportunity here is to try and maintain that kind of bandwidth density onto the fiber itself.
Tony, we've got 5 minutes till the Q&A.
Okay. Almost there. So finally, the point I want to make here is we talked a bit about how we see data centers evolving in their geographic distribution, and this AI at the edge is really giving rise to new connectivity technology demands to connect these regional data centers back to the main mothership hyperscale data centers themselves. So this is an area where we see the potential for low-cost, coherent optical connectivity to have an increasing demand. So the scale out of AI, again, creating opportunities for new connectivity technologies to proliferate. And we already talked about how chiplets in particular are enabling reductions in the cost and the size of coherent optical connectivity. So again, another example where you see great synergy between AI scale out and chiplet technologies. The last couple slides, I just want to give maybe a couple of use case examples to show how the chiplet ecosystem is evolving quickly to enable all this progress. So really, in the past, large monolithic chips were built out of many IP cores that had to be assembled as IP cores, maybe developed by different teams and then assembled into a very large monolithic die. And that model for designing big chips arose out of a desire to divide and conquer the growing challenge of designing these very complex systems on a chip. Chiplets can be looked at as a natural evolution, taking that to the next level. In addition to ameliorating the unsustainably high cost and risk of developing complete complex AI processors monolithically, once you make the jump and adopt a chiplet design paradigm, it unlocks all those other significant benefits we talked about. It allows you to go beyond the radical limit, put more compute and memory in a package. It allows you to make customizable, interoperable chiplets that allow for composable systems. And again, each can be fabricated and pre-validated in its own optimized technology, and each can proceed on its own development timeline without multiplying risks. But the key to enabling all this are those die-to-die interfaces that allow chiplets to work together as if they were one large die. So again, that requires interfaces with high bandwidth density, low power consumption, low latency, and that are very robust and interoperable to really enable the next wave of progress here. So quickly, I just want to use this as an opportunity to give an example of Alphawave's experience as an interesting case study of what the industry might look like in a couple of years. Rather than wait around for this chiplet ecosystem to emerge, Alphawave developed a portfolio of chiplets housing pre-validated IP to help accelerate the development of AI solutions. So there's an I/O chiplet that houses a multi-standard transceiver on one side and a die-to-die interface on the other side. There's a compute chiplet, again, with die-to-die interfaces, and then high-performance ARM-based compute cores to serve as an accelerator. And a memory expansion chiplet that allows for sort of an interface between UCI Express die-to-die interfaces and low latency memory interfaces outside the package. So I think that's really a great example of the way the chiplet ecosystem might evolve in the future. And all this is coming a lot faster, honestly, than any of us even thought it would. Again, supercharged by the rollout of AI. So as I conclude here, I just want to leave you with these key points, right? Chiplets are enabling customized silicon solutions optimized for AI workloads. And that's really essential because it's the only way to affordably scale performance, lower the power, and accelerate the time to market for these new bespoke solutions. Meanwhile, AI is redefining data center infrastructure. These connectivity technologies are evolving in order to allow AI clusters to scale up and scale out, as well as allowing for these geographically distributed data centers. And then finally, this chiplet ecosystem is emerging, enabled by die-to-die interfaces to support all of it. With that, I've hopefully got time to take some of your questions. Thanks
Thank you,
very much.
Thank you, Tony. Superb. I've got 3 questions in the Slack. Marvin asks, what is the substrate size required for this type of silicon photonics, and what type of substrate, and also what are the protocols you expect to use between chiplets over UCIe?
Right. So, I mean, I think everyone's first preference is to keep costs down. So, we see early chiplet-based designs using pretty standard packaging substrates. However, again, as more advanced packaging technologies become more and more mainstream, people get more and more comfort with them as more and more success making large designs with advanced packaging substrates, more and more capacity becomes available. You're going to, I think, quickly see a migration to those more and more advanced packaging technologies. But again, the early design starts we see were with standard packaging substrates. Some of the other questions there were about the protocols that might be used here. Again, UCI Express, I think, has really been a game changer for chiplet ecosystem. You know, it's certainly the number of requests and inquiries we get about UCI Express quickly surpassed, went from nothing to quickly surpassing any of the other IPs that we offer at Alphawave. So it's quickly become our most popular IP. So I think that's an indication of where things are at right now. Going forward, I think, though, that things are moving quickly, right? Packaging technologies continue to emerge. The demands of AI are looking for die-to-die interfaces with lower latencies. So, you never know what the future will hold. There's so much investment being poured into this area now that things are evolving quickly.
Okay, thank you. The next question from Craig. Can you comment on the typical UCIe bit rate and how that impacts, 1, the area impact due to low frequency SerDes logic, and 2, overall die-to-die latency, including error correction latency?
Mm-hmm. So UCIe interfaces operate, version 1 of the standard is at 16 gigabits per second per wire, and now moving to 32 gigabits per second per wire. And there's even early discussion on what comes beyond that. The footprint for those UCIe interfaces and the bump map is defined as part of the standard. There's bump maps and footprints defined for both standard package and advanced packages where there's a denser bump map and denser footprint. So that's all sort of pre-baked into the standard. And as I said, the bandwidth, the density that's achievable using those die-to-die interfaces is significantly higher than what you typically see with serialized I/O transceivers that operate at 100 or 200 gigabits per second. Hopefully that I think captures most of your question.
And then the last question was for me. An earlier talk today indicated, if I got my notes correct, UCIe for fixed unidirectional die-to-die links and bunch of wires for the 3 varieties of bidirectional links. Where do you see a role for bunch of wires in place of UCIe?
So again, I think right now, I mean, all the interest we're seeing is, or the vast majority anyways, on UCI Express. But this is an area that's been evolving quickly, and demands are there for something a little different, something that's more streamlined. So it's I think the door is open there for other use cases, but right now, I mean, we do see the majority of the interest for UCIe, and the UCIe consortium, where we do play an active role, is working on provisions that could handle all the next generation demands as well. So I think there's every possibility that that those links can scale to meet next generation demands too.
Okay, great. Thank you, everyone. There's no way you can do it. Please join me in thanking Tony for an outstanding keynote. Thanks, Tony.